we go.
Okay, so hi everybody. We are keeping this first slide as per instruction while waiting for people to join. So we will have this slide for about 1 minute. Then we will start our presentation. "30 seconds. Okay, still a few seconds.
I feel like we need a countdown.
Yeah, maybe that would have been good. Okay, 10 seconds. Like we can do this vocally. So 5, 4, 3. Okay, 1 minute has gone, so I hope it's enough. So this is a joint presentation by me, Paolo, from Linaro. I'm an external collaborator of Linaro and an assistant professor at the University of Modena and Reggio Emilia, and by Tim Walker from Seagate Technology. Yeah. Okay, we have been asked to show ourselves during the presentation. It's a little bit complicated because Tim is somewhere else, so we can just say hello and then I will, we will show a solution for boosting the throughput of multi-actuator drives. The idea is basically to fully utilize the bandwidth that these devices can reach. As I said, this is a joint presentation. The first part of the presentation will be an introduction of the technology for which we have developed this solution, so these multi-actuator drives, and Tim will take care of this part. Then I'll show you our solution. This solution is basically an extension of the BFQ IO scheduler, and then I'll show you some results, and I don't know, maybe Tim will tell something else at the end of the presentation, or maybe also during my part if I need some help. So, Tim, up to you.
Hey, my name is Tim Walker. I work for Seagate Research, and my job is I work with our key customers in implementing our new technology. And why did Seagate introduce multi-actuator drives a couple of years ago? It's because of the IOPS per terabyte limitations we've run into, which causes stranded capacity on drives. Well, if you look at this chart, you see that over the years, the hard drive capacity has increased a lot, and with the new recording technologies, it's looking to really go up. But the basic servo-mechanical capabilities of moving an actuator and positioning an actuator over a track hasn't kept up with the amount of data that it stores on the platter. So the number of IOPS, or IO operations per second, that you can mechanically do on a drive is staying about the same, yet the drive has a lot more capacity on it. So when you have, imagine, easy to understand, if you have, many more pictures on there that have been distributed out to many more customers, the customers all end up having to wait in line to get through a single actuator to get access to the data. And that's in storage, we call it IOPS per terabyte, and it's an important metric. And now there's been some improvements on the system requirements. Improved caching and data management has reduced the IOPS per terabyte required from the drives, but they haven't reduced it fast enough to keep up with the degradation. So that's why we introduced a multi-actuator drive by providing 2 actuators. Then we can divide the workload up between 2, and essentially, over most workloads, double the IOPS per terabyte. Next slide, please. high-level architecture of the Seagate implementation of a dual actuator SATA interface drive. Initially, Seagate released it as a SAS, where had two LUNs, logical units, which is the basic level of storage at the device, and each LUN was mapped to a single actuator, and you just literally drove the workload to them independently. That's tougher to integrate and higher cost. Our customers wanted the easier to integrate SATA interface. SATA doesn't support LUNs. A SATA device only has one address space or one namespace, and all I/O is within that address space. So what Seagate did was divide the address space into half, and the lower half of the address space is mapped. Those sectors are mapped to the lower actuator, and the upper half of the address space is mapped to the upper actuator. They're still fundamentally independent, with independent servos, independent read channels, etc. Where they're really common, though, is at the interface, and more specifically in the hardware command queue. SATA has a hardware command queue where you can queue up commands in the device. It's important for device performance because the device sorts those commands and completes them in the optimal order to increase throughput and decrease latency. 32 slots is plenty for most workloads, but when you divide that amongst two, then the 16 slots is getting kind of low. And plus, since it's a shared resource, unless we actively manage who's using it, then it will become, unshared. And the workload going to one side of the address space or one actuator can fill the queue and cause a denial to the other actuator and cause that actuator to go idle. And that's what we're really trying to detect and avoid, is the case where there is work for an actuator up in the OS stack, yet there's no room in the 32-slot queue for those commands. How do we make sure that as long as there's work available for an actuator, that the actuator gets the commands in its hardware queue so that it can action those commands?
May I, Tim? Yeah.
I'm ready for questions, yes.
So, this is exactly what happens if you don't control the load over the actuators. So, this is a grid. The large rectangle is actually a grid in which each cell represents one of the possible combinations of load over two actuators. One is the upper actuator, the other one is the lower actuator. The load on the actuator is actually measured in number of requests queued for that actuator. So we have this upper queue depth and lower queue depth. So basically, for example, the cell in the left upper corner represent the combination in which we have zero requests, so zero load for the lower actuator, and 31, I would say, or 32 requests for the upper actuator. So full load for the upper actuator, no load for the lower actuator. Each cell is colored, so this is a heat map. Each cell is colored, and the color represents the probability for that combination. And in this heat map, we see that with this workload made of small reads competing with other small reads, so basically the first set of reads, sequence of reads is for one actuator, while the other sequence of reads is for the other actuator, and they are issued in parallel. In this case, we see that without any control on the load of the actuator, it happens that only one of the two actuators is actually used. It's the upper actuator, because its queue depth is maximum during all the duration of this test, while the Q depth for the other actuator is 0. So without control, in this specific case that we wanted to show you, we have one of the two actuators completely idle. We are in a very bad usage situation for this drive. This evidently limits the throughput. This has an important effect, may have a dramatic effect on throughput. And what we need is to control the load on the actuator. So decide how to properly send requests to both actuators, in this case with two actuators. So it's a control problem and a problem of controlling I/O. And in this respect, there is already a component for controlling I/O. This component is an I/O scheduler. So an I/O scheduler is a natural candidate for implementing also proper control on the load of the actuators. An I/O scheduler decides the order in which I/O requests are to be served, in the same way as a traffic policeman controls the order in which cars cross an intersection, and so it decides who uses the shared resource intersection. An I/O scheduler works in the same way for the shared resource drive. The goal of an I/O scheduler has several goals. One is to guarantee a high throughput, but also to guarantee a low latency, hopefully a high responsiveness for the applications that need I/O for their tasks, give a fair access to the resource, and other goals. What is important for our problem is that the scheduler which we want to use to implement also a control on the load of the actuator should provide a good ground for implementing the extra policies for the actuator, and it must allow us to implement some accurate control, because this is what we want. In this respect, another option would have been to implement this kind of control of the load directly in user space. The problem is that if we do this in user space, then somehow we have applications that try to do their best in isolation, but the problem in the end is that there is a common point where all applications will compete for the drive. So once again, unless applications somehow coordinate among each other, we still have the problem that some application could have load, for example, for only one actuator, the other only for the other actuator, and so we still need a centralized point where we make sure that both actuators are somehow used and not only one of them. Okay, so this scheduler seems a better option because it already sits exactly where all I/O arrives. So it has full control on all the I/O produced by all the application, all the processes in the system. So that said, which I/O scheduler to use? In Linux we have several I/O schedulers. One of them is the BFQ I/O scheduler. And this seems a good candidate exactly because it has a rich infrastructure. So this could actually provide a good ground for implementing some logic for controlling I/O. And how is this infrastructure? It's this one. Basically, processes do their read or write operation. Of course, this is a simplified scheme, just to give you the idea. So let's say that simply processes do read or write operation, that we have I/O layers that translate these operations into I/O requests. Then the scheduler receives these I/O requests and classifies them into separate flows of requests. This is exactly what the BFQ I/O scheduler does. So it separates this overall sequence of I/O requests. It separates it it divides it into separate flows of I/O, and it queues the requests for each flow in a separate, dedicated request queue. the requests inside each queue are then scheduled by a per queue scheduler, and usually the order in which these requests are extracted from these queues is the typical elevator order. So they are extracted in such a way that the number of seeks of the drive is minimized. So this happens internally for each queue, but overall the BFQ IO scheduler has a flow service loop. So basically BFQ decides which flow to serve and serves that flow for a while. Then after a while BFQ switches to another flow, serves it for a while, and so on. Actually BFQ doesn't work in using time, but it uses number of sectors. So it basically serves each flow until a certain number of sectors for that flow have been read or written. Then it switches to the next flow, and so on and so on. This flow service loop basically decides the order in which to serve flow. So it's not like serving flow in a predefined order, but there is a scheduling logic that decides the order in which to serve these flows. The typical association between flows and processes is that BFQ creates one flow for each process. So basically each flow has its own queue inside BFQ. This queue is for the flow associated with the process, and from that queue requests will be removed and then dispatched to the storage device. Okay, this is what I've already told you. So we have a separate IO flow for each process and a separate queue, so for each process. This doesn't work, as I already showed you here, because this is the result. And this test has been executed exactly using BFQ, the original BFQ. This doesn't work, so the natural idea is just to split each queue into one queue for each actuator. That's it. So in blue here we have requests for the lower actuator, in red the requests for the upper actuator. If some process produces, creates, generates requests for both actuators, then some of these requests will be in one of the two queues, the other one in the other queue of the process. In general, if we have n actuators, each process will be associated with n actuators. And this is our first improvement, because this is how, for the same workload, the heat map changes. Now, we don't have only this case here, but we have both. So the two more or less equiprobable events cases, scenarios, are that either we have one actuator working or we have the other actuator working. The problem here is that we don't have anything in the middle, so having a few part of the requests for one actuator and the other requests for the other actuator. No, BFQ serves one queue for a certain amount of time, as I told you before. So what happens is that one queue with its color is served for a while. So only one actuator is used for a while. Then BFQ switches to another queue. If that queue has a different color, then the other actuator will be used for a while. But still, we have only one queue at a time in service in BFQ, so only one actuator at a time. This service scheme is perfect for this workload here if we have a single actuator, because it maximizes throughput. Because here we have a sequential workload, but this is not the optimal choice with a dual actuator, because in this case we keep one of the two actuators idle. This problem can be, this is only a part of the problem. The problem is more general. For example, we may have many queues that contain IO for a certain actuator and only one for the other actuator. And in that case, we have few requests served for that actuator with only one queue. Or we may have a queue with a high weight for one actuator and the other queues for the other actuator with a low weight. Also in that case, the other actuator is served only a little. For this reason, we have made a general solution, which is injecting IO. We found a threshold, a load threshold, such that if the load of an actuator is close to that threshold, but not higher than the threshold, we have that actuator is busy enough to be fully or also fully utilized. And at the same time, we don't steal too many loads to the other actuators, so we don't steal too much bandwidth to the other actuators. So when the IO stack asks for a new IO to dispatch, BFQ basically checks whether the current queue in service has IO exactly for the actuator that we don't want to keep under the threshold, which the actuator which is suffering for a too low load. If that queue is already the right one to serve, then BFQ dispatches IO from that queue. In case that queue does not contain IO for the actuator that is too low in terms of load, that has a too low load, then BFQ looks for a request for that other actuator in the other queues. If it finds some request in the other queue, then BFQ injects IO from those other queues instead of picking it from the queue that is currently in service. This is to try to keep all actuators utilized. As an initial threshold we tried before, and this is the result. As you can see with the heat map, now we have that none of the actuator is ever idle. We are around this threshold, this value of 4, both for the lower and for the upper actuator. And in terms of throughput, this is the results. This is BFQ with this injection implemented, and we have this. It's still for the same workload shown so far. These are the results with the other IO schedulers, and with BFQ without injection, just to show you the improvement that we get. Okay, this is more or less whole. This is still a preliminary contribution. Results cover just one cloud. We don't have production code available, and open issues are basically the first injection does not take bandwidth distribution into account, so we might have some unfairness. Another issue is what is the best value for injection. This probably depends on the workload, so maybe a dynamic threshold is better solution, or maybe we could settle with some static value that makes basically all workloads happy, and this option would reduce complexity. I think this is more or less all. I don't know, Tim, if you want to add anything.
Yep, I just wanted to add one thing, that the results we got were really good. The one point I think we need to clarify for our goals is that we are not remapping any IO to do load balancing across the actuators. We are ensuring that if an actuator has work to do in the system, that work gets presented to the actuator. It's the opposite. There are methodologies that would take a load and distribute it, by some algorithm across the actuators, but that's not the way we chose. We decided just to make sure with the injection that any given actuator never falls below a minimum queue depth. And by doing that, what we discovered was that we can keep that actuator very busy, even with a very low queue depth, not steal any IO from the other actuator, and the end result is we got a big improvement in throughput with very low impact to the latency and the performance on the other actuator.
Okay, we also finished our time, so.
Now we're supposed to stay on and wait for questions.
Yeah. So let's say goodbye from our video, then we will be the real one answering to questions.
Yep.
Okay, bye.